Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on complex numbers. So we know in maths, we usually can't square root -1. There's no number that you can square or times by itself to get -1. So to get around this, we just set the square root of -1 as this number I, this imaginary number. That's because sometimes in maths we need to solve problems that involve us square rooting negative numbers. So from this fact here, we get the set of complex numbers. The complex numbers are the set of all numbers a plus ib, where a and b are real numbers. So note the real numbers that we're used to, the real numbers is all the rationals and all the irrational numbers. They are a subset of the complex numbers. So an example of some complex numbers that are not real, a is 5 minus 12i, b is 4 plus 3i. So complex numbers are always real number plus or minus a real number times the square root of -1. So these are both known as Gaussian integers because both of these coefficients are integers. So let's look at performing operations with complex numbers. So adding complex numbers is easy. Again, just treat it like terms. So if I want to do a plus b, I add the two real parts. So 5 plus 4 is 9. And then I add the two imaginary parts. Negative 12i plus 3i just gives us negative 9i. All right, b minus a. So just be a little bit careful here because we've got our b, but we're minusing the whole of a. So we need to put it in brackets here. So again, we just kind of look at like terms. We do the imaginary and real parts separately. So 4 minus 5 is just negative 1. So here we have 3i minus 12i. Two negatives make a plus. I'm just left with 15i. So AB, which means A times B, we're going to multiply these two complex numbers using what we know about expanding brackets. So the way that we expand brackets, we go 5 times 4 is 20. 5 times 3i gives 15i. Now we take our second thing in the first bracket, negative 12i. Negative 12i times 4 is negative 48i. Now negative 12i times 3i. Well, negative 12 times 3 is negative 36, but I times I is negative 1. So this last term actually becomes positive 36. So the idea when you're expanding brackets like this, you need to multiply everything in the first bracket by everything in the second bracket. I need to take 5 and multiply it by each of these. Then I need to take negative 12i and multiply it by each of these. All right, let's now make this a little simpler. So we take the real and imaginary parts separately. So 20 plus 36 gives us 56. So 15i subtract 48i is negative 33i. So what about dividing complex numbers? Well, this is actually a bit of a challenge. Here we would have 5 minus 12i divided by 4 plus 3i. So it's not easy to do. We're going to use a pretty similar trick to what we use to rationalize denominators. Remember, when we have a fraction, we can times top and bottom by the same number. So again, using the difference of two squares, what I'm going to do is multiply by what is known as the complex conjugate. So the complex conjugate of 4 plus 3i is 4 minus 3i. Complex conjugates have the same coefficients, but a different sign in between them. So why would I bother multiplying by 4 minus 3i? Well, if we use our difference of two squares, we have a plus b times a minus b. The answer is just a squared minus b squared. The answer to 4 plus 3i times 4 minus 3i is just 4 squared minus 3i squared. So on top, using similar thing to what we did there, we have 5 times 4 equals 20 again. 5 times negative 3i. Negative 12 times negative 12i times 4. And then negative 12i times negative 3i is 36i squared. I squared is negative 1, so this becomes a negative 36. So on top, we have 20 minus 36 is negative 16. We have negative 15i minus 48i is negative 63i, so that goes on top. Now on the bottom, note that 3i squared is 9 times minus 1. This becomes 16 minus negative 9, which is 25. And you can see it's got a real denominator, and that's our final answer there. All right, the final thing we'll look at with complex numbers is looking at how to quantify their size. So let's say we have a equals 5 plus 12i. We want to calculate this, which we can think of as the size of a, because we want to be able to compare numbers. It's not easy to compare complex numbers. Is 5 plus 12i bigger than 6 plus 11i? So this process will allow us to determine that. So how are we going to do that? Well, what we're going to do is look at a random complex number, x equals m plus ni. The real part of x is just the real number by itself. The imaginary part of x is the coefficient of I. We can graph x, this complex number, on what's known as the Argand diagram. So if we have our real number x, the real part goes on the horizontal axis, the imaginary part goes on the vertical axis. We are going to calculate the size of a complex number as just the square root of m squared plus n squared. The square root of the real part squared plus the imaginary part squared. So why is that? Well, the number 5 plus 12i on the Argand diagram would lie here. Real part 5, imaginary part 12. So what we're essentially doing is calculating this length here. And of course, we can use Pythagoras. Of course, this distance is 5, this distance is 12, and the two axes are at right angles to each other. So using Pythagoras, this length here is just going to be the square root of 12 squared plus 5 squared. It's going to be the square root of 169, which is 13. The size of a here is said to be 13 because square root of 5 squared plus 12 squared gives me 13. And that will allow us to compare the size of complex numbers. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.